Hello. This next session is on artificial intelligence and medicine. I'm going to assume this audience is probably more medicine and less artificial intelligence, so we're going to structure it to sort of, with that assumption. I'll get closer. And this part I don't need to tell everyone, but the research in medicine and the application of medicine obviously is going through an enormous growth of complexity, the sheer amount of data, all of the different disciplines that need to be integrated. And I think Hiroaki will talk about this a little bit in his talks. I hope not to steal too much of his points, but I think he was saying something once that there are about 1 million papers in life sciences now a year. So you've sort of exceeded the capacity for a human being to literally read all of the papers. And what's interesting, and at the Media Lab, we work a lot now in life sciences and biology, because we're also finding one of the things that we do at the Media Lab a lot is build tools and think about things in different ways. And what's amazing is really, whether you're talking about the research or the diagnostics or the therapeutics, the number of different disciplines and the number of different tools that are now coming to bear on this discipline. And at the Media Lab, we call it sort of an anti-discipline, when you are no longer able to contain it in a discipline. And I think one of the most interesting tools that we have available to us to both manage and understand, in quotes, this explosively complex field is through artificial intelligence, and a lot of us like to call it machine learning. And artificial intelligence is a funny word because it's been around for a long time. Danny's mentor, Marvin Minsky, was talking about it before many of you were born, probably. But we'll talk about the different categories, but artificial intelligence encompasses a whole range of things where when it feels like computers are thinking. The stuff that you see really being applied effectively the most these days are a relatively narrow set of tools that we would call machine learning, whether we're talking about self-driving cars or the ability for Google to provide search results. But these are things that where machines take lots of data and are able to make some sort of sense out of it, or to be able to give you some sort of answers to questions. We'll describe a little bit about the different categories. There definitely are more, so computers are getting better and better at answering questions where lots of data is involved in figuring out the answer. And it kind of feels like magic because human beings aren't particularly good at it. There are other things like computers asking questions, which we'll talk about, which is a little bit harder. And the more it becomes something that human beings are good at, it turns out it's often that computers aren't as good at. And so one of the things we want to talk about a little bit, or be the focus of where we're going to end up, is sort of the role of machines in medical research, and sort of by extension, the role of human beings in the research of medicine. And so what does the scientist of the future look like? What does the machine of the future look like? What's the time horizon of that? And we want to give you some examples so you can get your head around it. So the order that we're going to do it is Hiroaki, who's, and we've got a pretty unique group of people. So Hiroaki, his background is in artificial intelligence. He created the Aibo at Sony, which was, if you remember, is a robot, and created the RoboCup, which was a robot competition, but for the last few decades has been a systems biologist. And Danny Hillis, who invented the connection machine at MIT, has also been working a lot in biology, but is sort of a man of many talents. And Finale, who teaches machine learning and focusing a lot of her energy on medical research right now here at Harvard. And they will, I think, will be able to get a very good view of the space. So the orders, I want to get Hiroaki to give you the RoboCup story first, because that'll give you kind of a sense of what traditional machine learning or AI can do. And then we'll get Danny to talk more about sort of extended intelligence and the relationship between humans and machines. And Finale can talk about her work in applying machine learning to research. And then we'll come back to Hiroaki on how machines might ask questions, and we'll do a panel. So with that, Hiroaki, maybe you can come up.
Spent like 3 to 5 minutes talking about progress in AI in the past decade, and AI has been. The history AI has been characterized in one way by the grand challenges. Like people think intelligent machines should be able to play the game like a chess. So, it's like at the beginning of the AI research, chess has been one of the major challenges, and it took a while for us to actually took like 50 years since the ENIAC to actually build a machine that can play the chess and beat best human in the world. So like in 1997, IBM Deep Blue won a Kasparov, and then after a while, actually 15 years, we got shogi, Japanese version of chess, beating one of the best shogi players in Japan. And then we witness, a couple months ago, AlphaGo actually beating one of the Go champions. What is interesting at that time is like in a chess, Kasparov think he recognized he made a mistake, and he complains that machine don't make mistake, and he get tired, machine don't get tired. So like he attributed like his loss as the human weakness. And the shogi and the Go actually is interesting because like a player couldn't understand why they are losing. So like, and then the machine is actually can envisions what people cannot do. So that's actually a big difference. And now actually Jeopardy, the quiz show, that's been won already. And we're talking about like autonomous driving and the RoboCup, this is soccer, which is more on the open-ended natural environment. So the RoboCup, this is an initiative I created like 18 years ago. And the goal was that by 2050, building a team of fully autonomous human robot, which win against the human World Cup champion, and then the official regulation of FIFA. So basically, this is about creating a soccer robot and try to actually use the technology built, towards this goal for the other domains. So I'd like to show you some of the video from the first year of the RoboCup. Oops, cursor here. 1997. This is the first year. Robot is not moving. So like this is, let's say like this is the World Cup robot. So like a BBC, CNN, NHK, all there, and that's like filming this robot which is not moving at all. Now 2014, this is like 2 years ago. Now this is it's just moving and in a great teamwork and very agile. So this robot is not remote control. They have their own sensor. They actually understand the environment. They make decisions. They make teamwork coordinations, and they go for it. So like after the game started, the people cannot really touch anything. You're just watching it. Those robots actually make decisions and play the game. Now, so oops, and this is actually the small size. There are a couple other size configurations. This is a small robot, but like it's fully autonomous. If you look at some of the shooting patterns, they actually make a really good teamwork. Actually, they stand they back up and then they score, right? So that's the interesting thing about this is that you can actually use fully autonomous robot team against the 6 or 7 people actually just controlling this robot as like a drones, like you can do the joystick. And then what happened is, in that case, human control robot cannot even touch the ball. And they can actually make decisions in a sub-millisecond order, which we can't. So like in that case, we have no chance of winning or no chance of touching the ball at all. Or the only time you can touch is like a robot actually make a mistake and shoot onto a robot. And that's the time like you can just touch the ball. So this is like a very okay. So that's the status. And then some of the applications, the early days actually the guy and the Cornell, Professor Cornell actually used this technology to have the warehouse management, and they created a company called the Kiva Systems. And that was acquired by Amazon, which is now Amazon Robotics, actually. Now, so like what they do is instead of chasing after the balls, they actually created this kind of robot to actually autonomously move those commodities and around the warehouse. So the traditional warehouse management robot has been more structured, central control. This is fully distributed control, and they can make decisions. Depends on the purchase order, which one to actually, cargo to be bring it to the picking station in which order, so the human can just, pick the thing and then package in Amazon and ship out. So like this is Amazon warehouse now, pretty much like automated. Now, and then also like I got this Aibo robot, which I getting involved, and so this is like old good film from the eyeball league, which in RoboCup, so like people just programmed eyeball. This is all the same hardware control, provided by the Sony, and just like all the researcher provide the program for that. And actually, they are not going to program how to behave. They actually program learning system and they train the eyeball or train the robot. The old robot you see in the recent day is no one programming it. They actually been trained to play that. In the early days, which is when you saw like an immovable robot, actually that's the day we have been programming how the robot should behave. Nowadays, we don't program that way. We just like train the robot. So that's actually a big change happening now. So what's the implication is the medicine here? This is, I won't be able to go into detail because this is unpublished data. Some of the machine learning can be used to classify the patient. So this is one of the therapeutic area. We classify the patient in 30 group. And then now, this patient group actually, current therapy is they apply some medicines for all the categories. But by machine learning, we can actually stratify into the 3 groups, which is effective, less effective, which actually relapse, or remissions, which is very effective. And this has been not known, and this is a new discovery, and we actually go down to the 3 biomarkers to be able to distinguish that. This is yet another therapeutic area. We can actually see this group can be stratified into the 3 categories, but if you look at this, the outliers and some of them transitions, some maybe some new subgroups. So like by having unsupervised learning, applying some of the technology we use for the robotic behavior control, we can apply the same machine learning technique to very specifically classify the patient. And that actually because of the cognitive limitations we have. And then I'd like to actually spend a couple of last slides and this introductory in an interesting case of how the robot, the AI can see something we cannot see. This is the original image on the left. It's a school bus. And the deep learning neural net actually trained to recognize this, right? So like there says this is the original image, the school bus. But the deep learning identified the right image as the school bus and ostrich. And we don't see the ostrich at all. And the actual difference is actually middle. There's some specific shape of the noise, and this is being amplified. They detected that shape, and they recognize this is ostrich. And then if you wonder, it looks like this, right? So like, this is a case usually quoted as like a fragility or instability of the deep learning convolutional neural network image analysis. But at the same time, if you think about it carefully, this neural network actually is able to detect the image which we cannot. So this is kind of interesting implications and how we can actually use this for understanding the kind of patient group or disease categorization which we may not be able to recognize, but AI may be able to tell us the specific kind of categories. And those are the example, centipede, the jackfruits, and we have no ideas what's going on, but they recognize that. And actually, they are associated image with exactly that. So like, well-trained neural network system today, in some cases, we should be able to see what we cannot see. Okay, that's the current state of the art. Thank you very much.